Wanted to record a video about this particular problem here that deals with vectors. And the reason I want to record a video is because it's really important to get a thought process down behind what exactly it is that we're going to be doing with vectors and to represent those. The computations end up being pretty simple, but to get there requires a little bit of work. So in this particular scenario, we're told that a man wishes to row the shortest possible distance from north to south across a river that is flowing at 4 kilometers per hour from the east. Okay, so let me just represent that. So I'm going to represent a river here, and I'm going to try to draw it kind of like a river. And we have him in a boat here somewhere, and he wants to head this way, straight to the south shore, because he's going from north to south. And there is a current that is pushing this way at 4 kilometers per hour. Okay, and so what we know already is that he is going to be kind of traveling some, let me represent this vector this way as well. So here's the current vector, and so we can probably intuit from that that he'll probably be traveling along the diagonal. In fact, we're going to assume there's a one-to-one correspondence, that for every kilometer per hour, that will drag him in that direction 4 kilometers in 1 hour. So the first thing I'm going to do is represent these vectors on the graph. So I, of course, have my north, east, west, and south. And what I want to do first is I want to draw these vectors, represent them. So I'm going to do that with a vector here. So I'm going to think about him as being at the origin. And I know that from the origin that there is a vector that is going to be pushing him this way. Okay, and I'm going to denote that with a unit of 4. Okay, so we know that's 4 kilometers per hour. In fact, I'll give it units of 4 kilometers, and we'll just think about what's happening here in 1 hour, right? Because the ratio of 5 to 4 will be there no matter what amount of time passes. 2 hours will be 8 kilometers per hour. The river will be pushing him westbound, and then he will be able to row in 10 kilometers in those 2 hours, and that's a 10 to 8 or a 5 to 4 ratio. So the fact that these are rates does not really impact my result. Now, I know he wants to go directly this way. I'm not going to draw that vector yet because I know that he's not going to want to row that way. So the other thing that I want to determine is in what direction should he row so that he goes directly downward. Okay, so I know that I'm going to have 2 vectors here. One is this one, and one is going to be probably in this direction, right? Because he's going to need to correct for that current. So he's probably going to want to go, I'm going to roughly draw it here, and I'm going to draw this in green because I'm just trying to, well, I don't know if I'm going to be able to draw it in green. Let me try this. There we go. We'll do green. And he's going to want to go probably in this direction. Okay, so somehow in that direction. We don't exactly know how yet. So that's what we need to figure out. But what I do know is that when I sum these 2 vectors together, the red vector and the green vector, that I am going to want to get as a resultant something that falls along a vector that goes in the downward direction. So I want a resultant vector, and I'm going to draw this in a different color. Let's go with blue, and that vector is we want to go straight down. Okay, that's what we want. He wants to go directly north to south as much as possible. So this vector here is going to be that resultant vector. And what do I know about that vector? The only thing I can determine is that I know that his x component, that I don't want him traveling east and west. I want him moving directly downwards. If we were watching from above, even with that current, he might be steering this way, but he's going straight down. So it's going to have a 0 x component. And in terms of the y component here, I don't know. That's just going to be some value. So I'm going to put a c there to indicate that that's going to be some value. And not only that, but I know it's going to be a negative value. So c is going to be less than 0, right? Because I want to be traveling downwards, and in the xy plane, that is a negative component. What I also know is that the x component, or that, the red component, that's represented by a vector of the form 4, 0. I don't know what this green vector should be, but I want to make sure that he is going to have a 0x component. So I know already from that if I sum the x components, it needs to equal 0, and I have to ask myself 4 plus what gives me 0, and that, of course, is -4. So I know that he's going to be traveling in the southeast direction. And in this case, basically any negative value will do. So I'm going to call this value, in fact, I'm going to call this C, right? Because if he wants to go downwards, then he's going to need to, 0 plus C will give me a C value. So now I need to figure out what the C value is. Well, what do I know about this vector? Well, I only know that in 1 hour he will travel 5 kilometers that way. So if I start to think about the components of this vector, so there's the x component right there, and the y component is right there, and I know that this is -4, and what I don't know is this value of c. Okay, so I don't know that y component. And in order for that to determine that value, I'm going to have to use, well, a couple of things. Since I have two sides, I can use Pythagorean Theorem. And Pythagorean Theorem, of course, will tell me that -4 quantity squared plus c squared is going to give me the hypotenuse squared. Again, my right angle there. And so I know that c is going to be the square root of 25 minus 16. Okay, so that's going to be the square root of 9. And I know that, sorry, I should write the absolute value of c, but we're gonna just think about c as a value right now and correct the signage later. So because it's in the downward direction, I actually know c is going to end up being -9, the negative of that value. Okay, maybe I should put a negative there because I know a magnitude will always come out positive. So that tells me that c should be -9. So my vector of travel should be -4, -9, and that would represent that vector right there. Okay, so problem solved. We know which direction he could go in. We could figure out the angle right there by now using some basic trigonometry, but we'll skip that step here. We know that he's going to be heading southeast, yes. The second question asks us something a little bit more complex. It says, imagine that there is a 10-kilometer-hour wind coming from the southwest. Okay, so it's coming from down here, and it's going to be blowing this way, right? So we have a wind that's essentially going to be blowing directly from the southwest towards the northeast. So it's going to be kind of forcing him that way. So now if now he's going to have to correct his rowing in order for that to happen. We have 3 vectors here. So I'm going to pause for a second. I'm going to erase these things. So this vector here that's going to emanate, really it's going to push him in this direction, and that's going to be perfectly southeast. So I'm going to try to split this northeast quadrant so that basically they're trying to tell us that because it's coming from the southwest, we know this angle right here is going to be 45 degrees. Okay, and now I know that the sum of the 3 vectors, the vector in the direction he's going to go, plus the vector that's corresponding to the current plus the vector that's corresponding to the wind, I know those should add up to give me this third vector here. I'm going to write those down. So once again, what I have is I have the -4, 0 vector corresponding to the wind, to the current. Then I'm going to have the little pink vector here, which is going to correspond to the wind. And I'm going to have his row vector. Well, let's think about this. Where should he probably go? He should probably, it's going to be really hard to say whether it's in this quadrant or this quadrant, but because I know that the magnitude of this vector is 10 kilometers, I have a feeling that that the resultant vector would end up pulling him over here. So I'm going to guess for a second that that vector is going to either be in the 3rd or 4th quadrant. So there are my 2 options, and so here's my 3rd vector. I don't know much about that yet, but I know that this is his row vector, and now I can say that the sum of these 3 needs to equal the 4th vector, which is actually going to represent the direction in which he's moving. So let's represent that vector, and here is going to be that vector. Okay, so I know I want him to go straight down, or he wants to go straight down. And whoops, try to even that out a little bit. No, I can't. Okay, well, you get the idea. And so that vector right there is going to be the resultant vector. Well, again, what I know about that is I want it to have a 0 component, and I want it to have a negative value of c right there. So the wind vector, I've got to figure some things out about that. I can determine fully what that vector is because I have a magnitude of the vector, and I have an angle, so I can work backwards using right triangle trigonometry to figure out what these two sides are. So I know that cosine 10 cosine 45 degrees will give me the x component, and I know that 10 sine 45 degrees will give me the y component. So those will be the components of my vector. Both of those will come out to around 7.1. Okay, so because it's a 45-degree angle, we really don't need to compute this. We know they're going to be the same, but nonetheless, we could. The row vector, the direction in which it needs to row, well, we know that the only thing that we know about that is that that's going to be 5 kilometers per hour, or 5 kilometers long. So I know that the magnitude of this vector is going to be 5. I also know that I want the x components to zero out. So I have -4 here, 7.1 here. In order for these three x components to add up and give me 0, this will need to be -3.1. Well, this value is going to be fixed. It's going to be a fixed component because I know the magnitude of the vector needs to be 5 kilometers long. So I know that 5 squared is going to equal -3.1 squared. Plus this value, we'll just call this, we'll call this y for now, y squared, not to confuse it with this, because we know it's not going to be exactly equal to c. And so we have y is going to be the square root of 25 minus, and I can just write 3.1 squared because we're going to get a positive sign there anyway. This value comes out to about 3.9. Okay, so I know that I'm going to want that y component to be negative. Oh, and by the way, because of this negative component here, we know that this vector isn't going to be the correct one. Now that I know that my x component, excuse me, I take that back. We know that this one is going to not be the correct one because my x component is going to be negative. Now my y component must also be negative because it's in the third quadrant. So this will be -3.9, and it seems as though there's nothing left to determine but to assess the situation. I know what these three vectors have to be. This component had to be on the basis that I knew that the x components had to sum to 0. This -3.9 had to be on the basis that I knew that the vector had to be 5 units long. So I can't control any of these y components at all. What I notice is that if I add up these three components, I get something around 3.2. So when I actually add these together, I get 3.2. So rather than traveling downwards, if he does row in that at his current speed, he is going to be moving actually in the upward direction. So he doesn't have enough row power or enough row speed to overcome the speed of the wind. He will be forced upwards. So this is not part of the question, but an interesting extension of this is how fast must he row? So if I know that I want this vector here, if I know that I want these y components to add up to something that's negative, I'm going to want this to be at least something greater than -7.1. So I can say that I know that the row speed squared has to be equal to the square root of 3.1 squared plus 3.9 squared, or rather, excuse me, -7.1 squared, because I want this component to be greater than less than -7.1. I want it to be more negative than 7.1. So that comes out to about 7.75. So this should be R. So R should be about 7.75. And that's going to be in kilometers, but because that's just over the course of 1 hour, I can add the units of kilometers per hour. So he needs to be going at least 7.75 kilometers per hour. So he needs speed, the row speed needs to be greater than 7.75 kilometers per hour. I don't want to say it has to be 7.76, because it could be 7.71, 7.751, and he would still be able to overcome that row and get a slightly negative component. He may not be rowing fast towards the shore, but he would still accomplish that. So all kinds of dynamics in this problem and all kinds of really interesting things to focus on, but the primary objective is to ask yourself, okay, what is it that I want to accomplish? What is the resultant vector that I want? What vectors are at play, and what do I know about them?